All right, we are asked to determine if the following system is consistent. So first off, we're going to write this thing as an augmented matrix. And we're going to go 1, minus 3, 1, 1, 2, minus 1, minus 2, 2, 1, 2, minus 3, minus 1. Okay, so that is the initial goal. Sorry, that is the initial step, the augmented matrix. And now there's a lot of ways to think about this to move forward. We can use elementary row operations, and let me just tell you, the idea behind these and the idea that kind of drives how we work with these has a lot to do with the idea of eliminating a variable. You guys have solved linear systems before, and you might say, hey, let's try and eliminate one of these variables. Maybe let's try and eliminate the variable x3. All right. And so to do that, I would say, well, if I multiply the first equation by 2 and then I add that to the second equation, I'll kill the x3. Well, that corresponds to row operation. So my first row operation is I'm going to say I'm trying to get a 0 right there. I want to get rid of the x3. So I'm going to say 2 times, here, you know what, let's say it like this. 2 row 1 plus row 2, and I'm going to put that in for row 2. And that's an elementary row operation. That's the complicated one that I'm talking about. So what does that give me? Well, first off, notice that only row 2 is changing. So I can just write down row 1. It's still the same. 1, minus 3, 1, 1. And I can write down row 3. 1, 2, minus 3, minus 1. Those don't change. Row 2 is twice row 1 plus row 2. So here we go. I'm going to say this plus 2 times that one. Well, that's just 4. This one plus 2 times that one. So that's just minus 6 minus 1 is minus 7. I get a 0, and I get a 4. So that is an example of an elementary row operation. And you want to write down what you did each step, both for your sake and for the sake of your reader, which will often be me. So please actually bother to do that. Okay, so we eliminated the x3 in this equation. Notice that if I wanted, I could write down the system of equations that corresponds to this matrix. This equation is still right there. This equation is still right here, but this equation has changed. Now the equation would read 4x1 minus 7x2 equals 4. We got rid of x3 in this equation. Let's do the same for the bottom one. So now we're going to go something like this, and let's think about it. What do we want to do? I want to replace row 3. So I'm going to replace row 3, and I'm going to say, what, 3 times row 1 plus row 3, that's what's going to go into row 3. So row 1 isn't changing, 1, negative 3, 1, 1. Row 2 isn't changing, 4, minus 7, 0, 4. Row 3 is about to change, and what am I doing? I'm saying 3, row 1 plus row 3. Okay, so look here. Look back here to see how to do it. So 3 times row 1 plus row 3 gives me a 4. 3 times row 1 is negative 9 plus row 3 gives me a minus 7. Interesting. And then, of course, 3 times the 1 is 3 plus minus 3 gives me 0. 3 times row 1, so 3 times 1 is 1 plus minus 1 gives me a 2. And right away, you can actually see that this system is inconsistent. Because on the one hand, you have 4, whoops, I want my highlighter here. On the one hand, you have the equation 4x1 minus 7x2 equals 4. On the other hand, you have the equation 4x1 minus 7x2 equals 2. That can't happen. So you can already see at this point the equation is inconsistent, but I actually want to go a step further with you, because there's something that happens that's really clear when you know that there's no solution. So let's go one step further. Let's actually go ahead and let's switch these two rows. I'm going to switch the rows. So I'm going to write that by saying row 2 switch with row 3. So now I'm going to get 1 minus 3, 1, 1. And then I'm going to have 4 minus 7, 0, 2, and 4 minus 7, 0, 4. I don't have to do that. I did it honestly as much to show you the switch notation as anything else. Now what I want to do is I'm going to go ahead and I'm going to try to multiply this row by minus 1. And then I'm going to add it to that row. So my final operation here is going to be to say, I'm going to say minus row 2 plus row 3, and that's going to go into row 3. So writing down what you're doing actually helps you remember how to compute it. So you say minus 1 times the second row, add the third row, that goes in the third row. So I can go ahead and write down the first row because it's not changing. 1 minus 3, 1, 1. And the second row, it's not changing. 4 minus 7, 0, 2. The third row, let's see what happens. So minus and add, I get a 0, I get a 0, I get a 0, and I get a 2. And that is the point at which you can really clearly see no solution. So this, when you see this form, all the variables are 0, but the constant isn't 0, then there's no solution. Think about what that equation means. That actually means 0x1 plus 0x2 plus 0x3, which, by the way, that's just 0. 0 equals 2. That's a problem, right? So let me think about how to write that. That's what it's saying, and we'll put an exclamation point there. That can't happen. So this system is inconsistent, which means it has no solution. And we used elementary row operations to get us there. So we're going to talk about that in the next section, and you're going to be able to start practicing these right away. But these are one of our main tools. We'll learn how to use Mathematica to do this, but you need to be able to do it by hand as well. All right, I've got just a couple of more things to cover with you before we're done in this video. So in example 6, we're simply asked, is this a solution to the following system? And so you're a solution if we can take this, plug in 3 for x1, 4 for x2, and minus 2 for x3, and it should satisfy each one of these equations. So let's just check and see. So let's see. For the first one, I get 5 times 3 minus 4 plus 2 times minus 2, and you can check that that is indeed 7. It works. We're good to go. So the first equation checks out. Second, I plug it into the next one, and I get minus 2 times 3, and then I get plus 6 times 4, and then I get plus 9 times minus 2, and the claim is if this works, this should be 0. Well, it is. You can see you've got a minus 6 and a minus 18 is minus 24. This is 0. It works. For the final equation, you plug it in and you get minus 7 times 3 plus 5 times 4, and then we get minus 3 times minus 2. We're supposed to get negative 7, and we don't, right? Let's check it and see. You get minus 21 plus 20 is minus 1 plus 6, because minus 3 times minus 2 is plus 6. You actually end up with 7. So you have 7 equals negative 7. That's bad. So the answer is no. This is not a solution. All right, I would like you to pause the video and see if you can answer the questions in example 7. We're going to do a lot of these throughout the course to test if we're understanding the theory. So determine if the following statements are true or false. If you haven't paused the video, do so. Hopefully you went over these yourself. So a system of one linear equation in 2 variables is always consistent. Consistent means it has at least one solution. Well, if you have one equation in 2 variables, that's always going to give me a line, right? And that's it. There's only one line, and so solution sets to my system are points on the line. Well, of course there's always going to be points on the line. So this is true. Kind of a trick question. It seems kind of tricky, but if you think about it, it should make sense. Okay, A system of two linear equations and three variables is always consistent. So here you have an extra variable, one more variable than you do equations. Is that always consistent? And the answer is no, it need not be. And can you give me an example of one of those? Certainly. Here's an example. x1 plus x2 plus x3 equals 1, and x1 plus x2 plus x3 equals 2. This system, you can check, is actually inconsistent. And it's easy to see why, right? If you plug a number in here and you get 1, then you're certainly not going to get 2. All right, so if you're consistent, does that mean you have to have infinitely many solutions? Absolutely not. We said that being consistent just means that you have at least one solution, so that's false. A linear system can have exactly two solutions. Now, if you were paying attention and you remember, we said no, there's either one, there's infinitely many, or there's none. So you can't possibly have exactly two. A system of three equations in two variables is always inconsistent. Seems like it might be because you have more equations than variables, but that's actually false as well. And to see that, you just can have the same line repeated again and again. So I could have x plus y equals 1, 2x plus 2y equals 2, 3x plus 3y equals 3. There's a three equations, two variables, and it is consistent. All right, so I wanted to just end really quickly by showing you visually what these row operations are sort of doing. So visually, you're starting out, let's just work in 2 dimensions. You're starting out with lines that look like that. And in the end, when you eliminate, you're ending up with lines that look like this. And the difference is, when you have a vertical and a horizontal line, it's really easy to find their intersection point, right? X is, let's say that my x-axis is over here, and you can just say, well, I can read off x is whatever this x value is, and y is whatever that y value is. So visually, when you're doing these row operations, you're taking your system that's sort of slanted, and you are writing it like this, allowing you to write off x equals 1 and x2 equals 3, or whatever the case may be. So that's one thing. The second thing I want to end on is just a little sort of glimpse ahead to the next section, and that is this. Let's suppose that you have an augmented matrix and you've done row operations and you've gotten it down to something like this, maybe 1, 0, 1, 2, let's say 0, 1, minus 1, 5, and then 0, 0, 2, 10, something like that, okay? We're going to have a name for this sort of matrix. I won't say it now, but you can notice that I've sort of got, on the coefficient matrix, I've sort of got this triangle of zeros downstairs, and then along the diagonal it's non-zero. I just want you to realize that in this case, you can solve a system like this really easily. Because look at what the last equation is really saying. It's really saying 2x3 is 10, which means x3 has to be 5. Okay, that's coming from the first equation. The second equation says x2 minus x3 is 5. Well, you know x3 is 5. So x2 minus 5 is 5. So x2 has to be 10. And then the third equation, you get x1 plus x3 is 2. x1 plus 5 is 2. x1 has to be minus 3. So the point is, once you can row reduce your matrix down, it doesn't matter if there are ones here or not for the purpose of solving, as long as you get a row like this, where there's non-zero here and a number there, then you can easily solve for one of the variables and then plug it back in. What you're looking for no solution is when you have a bottom row that looks like 0, 0, 0, and then something non-zero, like a 7 there. That means no solution, whereas this is good news. You can actually solve that. Actually, and I put it here in x3, it'd be just as good if it was here or there, right? If you have 2 of the 3 zeroed out, then you can solve for one of your variables. So you guys are ready to do the homework, which I've posted on Teams, and great job. You're through the first section.